Alright guys, so in this video, I'm going to be going through an amount of substance question from an AQA A-level Chem past paper, right? Now this is actually from the 2015 specimen paper, so it's a bit of a weird one to be honest. I've actually never done this paper before, and I got requested to do it, so I thought I'd check it out, and I'm not going to lie to you guys, this is a absolutely filthy question. The first couple marks, 2-3 marks are fine, but then it just it just goes pure downhill from there. But we're going to stay positive. I've done all of the past papers from 2017 onwards, and none of the calculation amount of substance questions were as difficult as this one, just because the knowledge that they assume you have is quite obscure, and the way that they want you to look at the mole ratios is really weird. But without rambling and ranting on, let's start this one and read through the question. As always, I'll link the paper and the mark scheme down below in the description if you want to check it out yourself. And hopefully I can make you guys understand this a little bit better. Whew, right, where do we start? Let's just read the question and make note of the key variables. If you see something like this in your exam, don't freak out, just remain calm, deep breaths, we've got this. So vanadium is 50 centimeters cubed of a 0.8 moles per decimeter cubed solution of this guy right here, NH4VO3. And this reacts with 506 centimeters cubed of sulfur 4 oxide gas measured at 20 degrees Celsius and 98 kilopascals, right? Use this information to calculate the oxidation state of the vanadium in the solution after the reduction reaction with the sulfur 4 oxide. Now, explain your working, and as always, you're given this gas constant R, 8.31. So what I always try and preach in my amount of substance breakdown videos is, when in doubt, start with the moles. Even if you know what you're doing, just start with the moles, okay? So I'm going to make that as clear as day here. Start with moles. Okay, just keep that in mind. If you're not too good at these questions, hopefully you can scrape the first 2 marks because it just involves molar calculations, right? So I'm not going to go into the real nitty gritty of converting units and equations and stuff. I'm just going to throw it on the page because this is a very advanced question. Let's just jump into this. So our 2 molar equations that we should know, N equals CV, N equals M over MR, right? There is a third one related to the ideal gas equation, involves a little bit of rearranging. That's also a mole equation once you've rearranged it. Do you remember what that is? PV equals nRT, right? And if you want to rearrange this, we make this the subject, we make the lowercase n the moles the subject, take this to the other side and divide both sides, right? So it's going to be moles equals PV over RT. So that's 3 mole equations on the page. And we're actually given some variables here that we can use to work out the moles of the vanadium and the moles of the sulfur 4 oxide. So let's do that. So moles vanadium equals, here it's super easy. We have a volume variable here and a concentration variable here. Multiply them together, simple as that, right? So 0.8, I'm going to do the conc first, multiplied by 50, right? Convert units, decimeter cubed. I'm not going to go through that. I'm just going to do it. Times 10 to the minus 3, same as divide by 1,000. That's just the way I like to remember it. So let's do the next one first, and then we'll put it all in our calculator at the same time. So sulfur 4 oxide, right? This is sulfur dioxide. The reason being is, if we know that this is +4, right? We know the sulfur is +4. Oxide is always going to, oxygen is not always, but for the sake of AQA A-level and all examples really, it's going to be -2. So that means there's 1 sulfur and 2 oxygens to make sure that it's neutral, +4, -4. So we know it's sulfur dioxide, right? They haven't said that, but we can work it out. So sulfur dioxide is going to be this equation here, because we're given, let's change up to a nice green, we're given the temperature, we're given the pressure, and we're given the volume. And what else? We're given the constant R, right? So we can plug that straight into our calculator. The first 2 marks are pretty simple here. So let's do all of our variables. So pressure. Well, actually, before I do that, real quick, units. What are our units? So you need to be aware of what the units are within this expression so that you can convert as needed. I'm not going to go into too much detail, but first let's tick them off one by one. So PV, so we're going to pressure first, 98 kilopascals, 98. Can we leave it like that? No, we can't. We have to convert it into pascals, so times by 1,000, okay? And that's just because that's the standard unit of pressure for the ideal gas equation. Right, next up, volume. So that is 506, okay? Centimeters cubed, we don't want that. We want meters cubed, okay? Standard unit of pressure, sorry, not pressure, of volume for the ideal gas. So I'm going to divide that by 1,000,000, which is the same thing as times 10 to the minus 6. So I'm going to bracket that up so we don't mess up in the calculator. Divided by R, so that's easy, 8.31. Multiplied by T, so that's 20. Now, can we use the degrees Celsius unit? No, we can't. We need to convert to Kelvin. That's the standard unit in the ideal gas. And pretty much everything in chemistry is Kelvin, pretty much. Unless it's a change in temperature, but I won't go down that route. So all you need to do here is plus 273. Okay, degrees Celsius, Kelvin plus 273, so that's going to be 293. Whew. Okay, so chuck that into your calculator and you're going to get 0.04 mole for our moles of vanadium. And then we're going to get now I'm going to do this to a bunch of significant figures here or decimal places. You can just go to like 1 or 2 above where you need to be. So all of these is 3.3.3. So I'd go to 4, but I'm just going to chuck in a bunch here. So 20366 mole. So first 2 marks done, okay? This is where it really starts to get tricky. So this also involves transition metals, right? We have our vanadium up here, transition metal. So under the AQA spec, there are 4 oxidation states to vanadium, okay? So I'm going to write them down quickly. Got +5, +4, +3, and +2, okay? You should know these. Try and remember them if you want to get those top grades, right? So +5, what is this? This is going to be VO2 plus, or alternatively, VO3 minus. Okay, those are the 2 that it can be. +4, we're going to have VO2 plus, so that's a 2 plus charged ion overall for the compound. And then we're going to have V on its own, so vanadium 3 plus on its own, and then vanadium 2 plus on its own. That's the 4 you need to know, right? Obviously 5, I guess, but 4 different oxidation states that we need to be aware of. And that's what we need to do. We need to calculate the oxidation state of vanadium after it's been reduced. So there's a clue here, guys. We know that the sulfur, so this also involves redox, right? So if something reduces something else, it itself gets oxidized, oil rig, all that good stuff, right? So if the vanadium has been reduced, that means the sulfur 4 oxide, the sulfur within that compound has been oxidized, okay? So let's write that here. Vanadium reduced, sulfur oxidized. Okay, so this is reduction is gain of electrons. This is loss of electrons, okay? I know it's super basic, but I'm going to put it on the page just in case you're not aware. Okay, so first thing I'm going to do is I'm going to think to ourselves, what is the oxidation state of the vanadium within this compound right here? And then what I'm going to do is think, what is the oxidation state in this, right? And then we're going to reduce one, oxidize the other, and see what goes on. So NH4VO3, let's write that right here, NH4VO3, okay? Now, there are 2 methods to work out what the oxidation state of vanadium is within this compound. One is memory, one is process of elimination, right? So memory is this right here. So we've memorized that VO3 minus is +5 oxidation state for the vanadium. What does this look like? What does this look like right here? This is VO3 minus, so we know that this is +5 for this vanadium. Simple as that. Okay, so memory has, if you memorize that this right here was +5, we know that the vanadium in here is +5. Simple as that. If you don't remember that and you're like, oh man, I don't know what's going on. Remember ammonium ion, right? Ammonium ion NH4 plus. Okay, ammonia is NH3 neutral. Ammonium has gained 1 extra proton or hydrogen ion, so it's NH4 plus. So if we split this molecule in half here, we've got a plus over here. Oxygen is always -2 it's not always, but again, think of it as always -2. So 3 lots of -2 is -6. -6 plus 1 is -5. Therefore, the missing element here, vanadium, or the missing ion, is going to be +5. Okay, so 2 ways to work out what the oxidation state in our beginning reactant is that gets reduced, this guy right here, is going to be +5. Okay, and we'll use that later on. So we've worked out what vanadium is, so I'm going to tick that off over here. Next up is sulfur, okay? Now, sulfur is also group 6, just like oxygen. However, I'm not going to go into detail, but due to electronegativity, electron configuration, etc., oxygen, as I mentioned, is going to primarily be -2 oxidation state, but sulfur can have varying oxidation states, okay? Doesn't always have to be -2 due to electronegativity being less than oxygen, but it's going to have 4 oxidation states. If you remember this, that is great. You don't really have to, I'm not going to lie to you. So we can have -2, just like oxygen. We can have +2, we can have +4, we can have +6, okay? These are the 4 oxidation states that sulfur can exist in, depending on the conditions and reactions, etc., right? So, what are we starting with here? We know we're starting with a +4 all the way up here. It's told us in the question, right? So we know we're starting with this. So, if we know also that the vanadium is reduced and the sulfur is oxidized, we know that we're going to be having to go this way, okay? No point, we can just ignore these two because we know that it's not reducing, it's not gaining electrons, it's not getting a more negative charge from the electrons being added to it. We know it has to go this way. So we know it's going to become a sulfur with a +6, right? So in my head, right, in the exam, I would think to myself, okay, how can sulfur exist as a +6? It's going to either be SO4 2-, the sulfate ion, is going to be hydrogen sulfate. Sorry, that's not 2-, that's 1- right there. It's going to be sulfuric acid, or it's going to be SO3, okay? Now, this SO3, this sulfur trioxide, this can only be formed, as far as I'm aware, in the contact process. Okay, and it requires a catalyst, V2O5. Again, this is in the spec, you should know this. So I'm going to ignore this one for now because I don't know that, even though vanadium is present, I don't know if it's in this format and it hasn't told us that it's a catalyst. So even though also this is +5, so maybe you could connect some dots here and think, oh, okay, it could be SO3. It doesn't really matter. We know that the sulfur has to be -6. So in the mark scheme, it shows this guy, but in reality, I'm guessing you can pick any 4 of these and you could be okay, just based on the next stage of the question, right? So if I say, okay, SO2 is oxidized to SO4 2-. For the sake of this, I'm going to use the same ionic compound that it was mentioned in the mark scheme, but as I said, you can think of it as any 4 of these. As long as the sulfur is +6, you're all good to go, right? Now from here, you can follow the exact same step. I don't want to say exact same because I'm just lying to myself. You can follow the same step in terms of molar ratios, right? In all my videos, whether you've watched them or not, I always say 1, start with the moles, 2, mole ratios, right? What is the coefficient between the reactants and the products? And we know it's going from a +4 to a +6, so it has to lose 2 electrons. Now, you may be thinking, why the hell has he written it like this? That's because it's just standard in chemistry. You never minus things, right? You never minus things in a chemical equation, chemical formula. You're always going to add them, right? So I'm going to leave it like this. Now, this in this current form is a diabolical state, right? It's not balanced whatsoever, and you kind of want to ignore that for this question, I suppose, because it's in solution. I'm just doing this off the fly, but you can maybe balance it with water in some way. So let's say we had H2O here, and we're going to obviously have H+ ions to balance the charges. So it's going to be SO4 2- plus. We've got our 2 electrons plus H+. So there's 2 there, a bit 2 there to balance the 2 charges. Actually, we need 4 to make it neutral. So it's going to be 4- 4+, and then 2 here. That's 2 oxygens, 4 oxygens, 4 oxygens. Okay, so this is balanced. I don't know if this will be accepted or not, but I just quickly rushed that out so you could balance the charges and see what was going on here in solution. I'm going to rub this out because you can essentially ignore that, right? So all you're concerned with here is the mole ratio. You can essentially ignore that part that I just wrote. Let's just have 1 to 1 to 2. So that's our mole ratios here within this oxidation, right? Now this is where I say it just throws you off because I've done like I said, every single past paper, and I did my exams before 2016. I did them in 2015. I was the last year to do dual A-level, AS A-levels, and I've never seen a question like this. I've done all the past papers all the way back from like 2006. Never seen a past paper like this in terms of amount of substance question. They never consider the mole coefficient of the electrons. I've never seen it. Maybe there is if you go back and back and back, but I've never seen it. So this is why I assume they decided to get rid of it, because I'm guessing the examiner's report said like only a very small percentage of people got this. So if we look at this, we can say, okay, we know what the moles of the sulfur dioxide is, right? So moles sulfur dioxide, I'm actually going to do this as sulfur 4 plus equals, we can have 0.020366 moles, right? Therefore, the moles of the electrons equals this value right here, the moles of the sulfur 4 plus, times 2, okay? Times 2 just because it's molar ratio, okay? For every 1 mole of sulfur dioxide that is oxidized, 2 moles of electrons are produced or lost, however you want to look at it, okay? Lost. I'd go with lost rather than produced, especially if you're writing out an explanation. So that is the moles of electrons lost by sulfur in this oxidation reaction, okay? And if you put that in your calculator, or you can just do it in your head, it's going to be 0.040732, okay? And that's moles again, right? Whew. Okay, we made it this far. We know what the moles of electrons are that have been lost by the S4 plus, okay? So if, like I'm going back to oil rig, right? In redox, this has been oxidized. So we know what that's been oxidized by, and this has been reduced, okay? So we know that this has been oxidized and it has lost this moles of electrons. So if the sulfur has lost this moles of electrons, that has to be added onto the vanadium ion, okay, for it to be reduced in its equivalent state. However, something you have to consider here is the amount of things that are reacting. So as we worked out earlier, we have 0.04 mole of vanadium that is getting reduced, and it is gaining 0.04732 mole of electrons. However, what we want to think to ourselves is if an oxidation state is changing, it has to be an integer. So 1 mole of sulfur 4 plus has gone to 1 mole of sulfur 6 plus. In an equivalent way, in a paralleled way, 1 mole of vanadium 5 plus has gone to 1 mole of vanadium something, okay? So what we have to do here is very similar to empirical formula. We have to work out the ratio that is occurring for 1 mole of vanadium ions, okay? And this is when it gets real difficult. Firstly, you never do this. And secondly, you don't really work out the ratios of things that are being oxidized or reduced, okay? So it's kind of weird. So what I'm going to say here then, let's go back to nice blue here. Therefore, 0.040732 mole of electrons is gained by the 0.04 mole of the vanadium 5 plus ion, okay? What we want to do is to get it back to an integer, we need to divide one by the other. So how many moles of electrons has 1 mole of these vanadium 5 ions gained? Hopefully that makes sense, right? So what we need to do then is we need to do the moles of electrons divided by the moles of vanadium 5 plus, okay, that we've calculated. So what that's going to be then is 0.040732 divided by 0.04. Hopefully straight away you guys can see that these are pretty much the same number. If we just stick to like this number of decimal places, 2 dp's, 0.04 divided by 0.04, to the closest integer, this is going to be 1. Okay, so roughly 1 is our integer here. So what does that mean then? That means that 1 mole of vanadium 5 plus ions has gained 1 mole of electrons in this redox reaction. Okay, so if it's gained 1 electron, right, it's going to be going from a 5 plus to a 4 plus. Okay, so what I can say then is therefore vanadium 5 plus goes to vanadium 4 plus. Okay, so equals oxidation state of +4, or like this, however you want to put it, right? That would be our final answer. All right, guys, done. Whew. That is a difficult question, man. That is a real tough one. And the reason being, like I mentioned, is they never ask you this. They never ask you the mole ratios of electrons, at least as far as I've seen. And they never expect you to work out what the ratio is between the true ratio, but for 1 mole of an ion, okay? And that is how you would work out a change in oxidation state in this way, is you would have to think how many moles of the ion is reacting, how many moles of the electrons has either been gained, so reduced, or lost, oxidized, right? And you'd have to work out the ratio in this way to work out the actual true number of moles of electrons, and then you would either plus it or minus it from the starting charge, the starting oxidation state. But I hope that makes sense. I tried to explain it the best that I can. I tried to chuck in different ways of approaching the question, but I'm not going to lie to you. I'm going to say it straight. It's a very difficult question. So if you guys did this yourself and you got all 6 marks straight away without doing the mark scheme, just an absolute pat on the back, all right? That is some insane skills right there. But yeah, hopefully this helped you out. If you've been struggling, as I said, I was requested this question. So if you're watching, I hope you found it helpful. So yeah, guys, digest this. I'm not expecting something like this to come up again, but if you can do this question, you can do any amount of substance question. I'm not even joking. So if you did find it helpful, if you learned something, like the video, subscribe. It really helps the channel grow. Best of luck in your revision, guys, and your exams. Until next time, peace.